Hello everyone, this is Brendan again, and this video is going to go more in depth as to what atomic radius is and why the trends are what they are. So we know from the last video, or 2 videos ago, the lecture slides, that the atomic radius increases as you go from top to bottom. And right now I want to explain why that is. So when looking at atomic radius, as with all periodic trends, you really want to keep 2 things in mind. You want to keep the effective nuclear charge in mind, as well as the highest principal energy level. So both of these are going to come into play into all the videos. Let's explore why the atomic radius is larger for sodium than it is for lithium. Remember, sodium is 1 below lithium on the periodic table. We know lithium has 3 protons because its atomic number is 3. 3 plus, and we know sodium has 11. 11 plus. Well, when we're filling the energy levels of these atoms, it's important to look at the electron configuration. Lithium has an electron configuration of 1s2, 2s1. Using the Bohr model, which we know is not correct but helps to simplify our understanding of things, we can see that within the n equals 1 energy level there are 2 electrons, and within the n equals 2 energy level there are 1 electron. So I'm going to go ahead and place these electrons in. So there's 1 there, 1 there, and maybe 1 there. So what we can see is that the effective nuclear charge of the lithium atom would be the atomic number minus the number of inner electrons. So Z effective would equal 1 in this case, 3 minus the 2 inner electrons that are in the n equals 1 energy level. For sodium, the atomic number is 11, and there are 10 inner electrons. The electron configuration of sodium, 1s2, 2s2, 2p6, 3s1. So the only valence electron is in the n equals 3 energy level, and there's 1 of them. Within the inner electron levels, 1 and 2, there are a total of 10 electrons. So the Z effective for this would just be 1, the 11 for the atomic number, minus the 10 inner electrons that lie in the n equals 1 and n equals 2 energy levels. Alright, well, what gives, Brendan? Why would you even tell us that? That's useless information. In fact, it is. It really doesn't matter as you go down period. There's really no difference in Z effective. So that's not what's going to cause the difference here, but just a little extra practice with Z effective. What is going to cause the difference is the fact that sodium now has its valence electron in the n equals 3 energy level. If we were to fill these, we would have 2 in the n equals 1. We would have 1, 2, 3, 4, 5, 6, 7, 8 there, and we would have 1 in the n equals 3 energy level. Well, since the principal energy level corresponds to the average distance from the nucleus, the n equals 3 energy level would be further out than the n equals 2. So the valence in the sodium is further than the valence in the lithium, and that's what causes sodium to have a greater atomic radius than lithium, and explains the general increase as you go down a column within the periodic table. So the answer to this question here is new valence electrons. So new valence electrons in higher principal energy level. I'm going to write that as N. N represents the principal energy level. So that explains our trend as we go down a column. Now, what about as we go across? So here I'm giving fluorine and lithium as examples. Both of these are atoms that lie within the same row or the same period of the periodic table. Let's try to think about why this happens. Well, lithium has a charge of 3 plus. Fluorine has 9 protons, so this would be 9 plus. The electron configuration for fluorine and the electron configuration for lithium are what I've just written. Well, what we can see is that lithium has 2 inner electrons. Its valence shell is the n equals 2 energy level, so the inner electrons are in anything below that. So lithium has 2 inner electrons. Fluorine has 2 inner electrons as well. Looking at the picture here and looking at the number of principal energy levels, we can see that they're the same. They both have the n equals 1 and the n equals 2 energy levels. So whereas before that caused a difference, here that's not what's going to cause it. What is going to cause the difference is the Z effective. The Z effective for fluorine, the atomic number is 9 minus the number of inner electrons 2 is plus 7. For lithium, that Z effective is plus 1. Well, why would this make a difference? So basically these outer electrons in the fluorine atom are being contracted inward. The reason they're being contracted inward is because they're feeling a really strong positive charge, a really strong Z effective from the center. And that's what's going to cause lithium to effectively be smaller. Let's just fill these in. 2, 3, 4, 5, 6, 7. 1, 2, 3. So fluorine with that very large Z effective, I wish I could show you with my hands right now. I'm trying to. It's kind of funny to watch me, but it contracts inwards. It shrinks in as those electrons want to get close to that proton-rich center. So the reason it decreases from left to right across a period is because of the higher effective nuclear charge, the higher Z effective value.